Any questions?
What do we do on a lab when we have like a wrong like answer for like just all of our data? And we like if something wasn't zeroed out.
It depends. I mean, if your data is flawed, but you all agree on it, then potentially there's no penalty. It really depends on the situation.
Okay.
If all of you agree on the data, then there won't be a penalty for that. If you have something that's just, you didn't follow directions, and it's obvious that you didn't follow directions, there would be a penalty for that.
Feels like something wasn't like zeroed out before we got it, and then
Yeah, I think I'm gonna have to see it to figure that out.
okay.
But your calculation should be based upon your data. So if your data's flawed, your calculations, you'll get crappy answers in the end, but it should still be consistent with what you started with. I think that's probably as best I can do right now without seeing the specific situation. I assume that was a hypothetical, not necessarily reality.
Definitely, for
Okay.
sure. Only hypothetical.
Yeah. You have a friend who forgot to zero out.
Well, no, I heard one of my friends' labs with it.
Yeah. Any other questions? Well, whoever comes in late will have to knock, or they'll have to leave people in the hallway. All right, so we've talked about projectile motion, did a lab on that. We're basically finished with chapter 10. Anything I've missed should be in the videos. I'm gonna jump to 19. Waves. So first, let's just hit a couple vocab words. One of which I know we've dealt with before, period. It is the time for one cycle of repetitive motion. So the period for the Earth going around the sun is 1 year. The period for one Earth to rotate around its own axis, 1 day. Very roughly, the period for the moon to go around the Earth, 1 month. Or as we did in class the other day, 27 point something days. Frequency. This really is much better. How frequently? Repetitive motion occurs. And I know that you really should not use frequently when defining frequency. But frequency is a physics term, frequently is the English term. Wavelength. How far a wave travels in one period. Amplitude. with respect to the median of a wave.
What's that last word?
That
Or sorry, like the last.
amplitude, the magnitude, WRT, with respect to the median of a wave. There are people making noise, so I close the door. I'll turn it off. All right, so when expressing a wave, there are two basic kinds of waves that we will be dealing with. Longitudinal and transverse. So, longitudinal wave, here's an example of a longitudinal wave. All right, ordinary slinky. Basically, I'm gonna stretch this out, and then I'm gonna release some of the coils at the top once it calms down a little bit. What did you see? Again, I'm going to release some coils. Observations?
There's like a little like clump that is like moving up and down.
Okay, so that would be an example of a longitudinal wave. In this case, the particles, the things that are actually moving are the coils, but the coil up here didn't move down there. It was just that clump of coils, that sort of the higher density of coils. So in the longitudinal wave, the particles, and I'll put that in quotation marks because I mean, it could be coils or people or whatever you happen to have. The particles move parallel or anti-parallel to the wave. So the wave moved all the way down, moved all the way back, and the particles just moved up and down. That's parallel. Anti-parallel just means the opposite direction. Transverse wave, the particle moves perpendicular to the wave.
Wait, would anti-parallel not be perpendicular?
No, it's not. Parallel, same direction. Anti-parallel, opposite.
Oh, okay.
So an example of a transverse wave, and we're going to do it right now. We're going to start with Levi. So you need to get ready to stand up. Don't stand up quite yet. What's going to happen is Levi is going to stand up. When you use a little flourish with their hands, that's great. He's going to stand up, and when the people next to him, so that's going to be Caleb and Jakara, when they see him do that, they're going to go, and then just like in a stadium. And we're going to move that way. The wave's going to move that way. All right, so get ready. Levi, when you're ready. There seemed to be a lack of participation up front here. I'd like to see that done again, but this is get your blood flowing here. All right, Levi, do it again. How about a wave of just two? Let's get you moving. Grace, why don't you start? There we go. That is a transverse wave because the wave traveled that way, but you, the particles, moved up and down. So you moved this way, but the wave moved that way. So that is a transverse wave. Another example of transverse and longitudinal waves, sound actually. So let me put the slinky pulse here, slinky pulse. P waves. And what I mean by P waves is that in transverse waves, we have the sound. Transverse wave, we have S waves. And I think that's called the dynamic wave, or stadium wave. All right, so sound is a longitudinal wave because basically my vocal cords are vibrating back and forth, and my vocal cords will push molecules closer to each other, so we get that high density part, and then those will hit other particles, which hit other particles, which hit other particles, and eventually the sound gets to your ear. But what's coming out of my throat takes a while before it actually gets to you. But it hits other particles, which hit other particles, which hit other particles. And so in a longitudinal wave, you basically have a pushing and pulling in the direction of the wave. First it pushes particles together, and then it relaxes, tries to go back to what it was. Now the P wave happens in earthquakes. So if we've got a seismograph here, so this barrel will turn, and you basically have a needle on it that's etching into it. At least that's what they looked like a couple decades ago. If there's an earthquake down here, we have pressure waves, thus the P, or part of the reason for the P. You have these pressure waves that you have one part of the earth pressing into another part, which presses into another part, presses another part. So you have these P waves that go cruising through until they get here. They also, because they go through the core of the earth, they hit the seismograph first, so they are also primary waves. So P for pressure or primary. Also in an earthquake, you have land basically going like that. So you'll have this shift. Land will be moving like that, causing the land next to it to move, causing the next land to move. So the wave's going to be moving this way while the earth is moving up or down. And so those waves take longer to get there. So they are shear waves. Shear waves is when you have two bits of mass like that, and there's a push to the side. That's a shear wave. It also gets there second, so it's a secondary wave. In order for a transverse wave to work, it actually, as it pulls on, well, let's pull up the long coil. As this part of the coil moves up, it pulls the other part with it. And then that will move up, pulling the next part with it, and then that will move up. And so that in the transverse wave, there is a pulling on the part of the wave next to it, part of the material next to it. So transverse waves really don't travel particularly well in water and air. If transverse waves work well in gases, then you should be able to feel this. Feel that breeze coming right next to you just then? It doesn't work particularly well because when one gas molecule gets moved, it doesn't really drag others with it. Longitudinal waves do travel well in gas, otherwise you wouldn't hear me. And so this is how the geologists had some idea of what's in the center of the earth, because the longitudinal waves get there first. They can travel through the core of the earth. The secondary waves, or the shear waves, cannot travel through the core, and they have to go around the long way. And so from this, that's when we get this idea that the center of the earth is not solid. And that is close to all I know about geology, much to my wife's chagrin. Okay, questions to hear? All right, because I don't feel like writing words out, let's let's talk about the shorthand. Period, the symbol for period, capital T. So what would be the standard, international standard unit of period?
Seconds?
Yes. Frequency. There's two symbols that are basically out there. The symbol that I use is the one that you most likely will see. I use the same symbol as I use for friction. But frequency, basically a Baroque F. The other symbol, if you've seen the video, sorry, it's repetitive. The other symbol you'll see is the Greek letter nu, which looks a whole lot like a V. In some fonts, nu looks like that. In other fonts, nu looks like that. Matter of fact, the font where that's a nu, V looks like this. And in the font where that's a V, in the fonts where that's a nu, V looks like that. It is very confusing. And the only reason I mention this is just in case you happen to run across it. My first year here, I had a student who was doing some of the nanotech stuff and was confused about why an equation had two V's in it, when in fact one was a V and the other one was not. One was a nu. And so that probably is the last time those will be mentioned. So frequency, the SI unit of frequency. Capital H, lowercase z. Hertz. Named after? Take a wild guess.
Hertz.
Yeah. Heinrich? Maybe. He was the one who discovered that electromagnetic waves physically exist. All right, now what exactly is a hertz? Well, period is the time it takes for a cycle, so it's seconds per cycle. Frequency is the number of cycles per second. So how frequently something occurs is basically how many times per unit time. So a hertz and a second are just reciprocals of each other. So 1/seconds equals a hertz, or probably better, 1 cycle per second is equal to a hertz. And a matter of fact, the period is the reciprocal of the frequency. Or frequency is the reciprocal of the period. All right. Wavelength, the symbol, is a lambda. And again, here's the thought process. Wavelength is a length. What Greek letter begins with the L sound, like length? Lambda. So they use a lambda. It is a lowercase lambda. The SI unit for wavelength. Here's a hint, wavelength.
Centimeters?
It is. Amplitude, the symbol I typically use if I'm just talking about generic amplitude is just the capital A. I can't really come up with a specific unit for amplitude because it really depends upon the situation. For sound, it could be pressure or decibels, or which I guess is intensity. For a transverse wave, we'll demonstrate one out in the hallway. Probably just physically a measurement of how far it goes. All right, any questions to hear? Then let's head out into the hallway. I will need one volunteer. Come on. Feel free to hit pause. For those just tuning in, mass of the string, the length of the string. So it turns out this thing's vibrating 60 times a second, and that's recording basically 60 frames a second. And so when you look at it, it looked like the string wasn't moving at all. There we go.
I saw it, yeah, okay, because I saw it, I was like, but it has like 3 days.
So just start out with turning this thing back on. All right, as I apply force, hopefully you can see that. That's second harmonic. I assume you can see it. Let's see what kind of coordination I can muster up here.